Hello, my student. This is the second part of chapter 2 on the analysis of statically determinate structure. I hope the first part of this chapter is not so tough for you. In conclusion, for the first part of this chapter, we do study on the modeling of the structure. Being an engineer, we are create our imagination to be the real structure. By doing that, we need to model all the structure into the physical thing. By modeling, that means you got to put part of the structure together. That means put the beam into the column and put the floor onto the beam. For example, let's consider this structure. This is the roof deck of the single-story building. It has the RC floor built on the steel frame. By construction this structure, we got to build all the foundation, and then we construct the column, and then we put the beam between the column. We view each frame, and then we connect each frame by the small beam, linking them together. Based up on this, we build the floor on the top of the building. The load from the floor will transfer to the small beam, and the reaction from the small beam will transfer to the girder of the frame, and then the reaction of the girder will transfer to the column and then to the foundation of the building. Okay, this problem set the rate load and live load acting on the floor to be 4.5 kilonewton per square meter. It asks us to determine the distributed loading that act on the small beam DI, or you may call this as the purlin, and then the distribution of the force that act on the beam A, B, C, D, E, F, G. By doing this, we need to assume each connection of the beam are pin and roller. So that means all the beam here gonna consider to be the simple beam, and then we will transfer the force to the pink beam. Oh no, sorry, the force to the red beam and to the pink beam and to the column. And finally, we may draw the shear diagram and moment diagram to find the Vmax and Mmax of the beam. And by doing this, let us go to this picture. Again, the load from the floor transfer to the red beam, the load from the red beam transfer to the pink beam, and the load from the pink beam will transfer to the column. Let us first consider the beam DI, and we should first check the force that's transfer from the floor to the beam DI is going to be one-way action or two-way action. By doing so, we got to consider the area that's cover the beam. By doing this, the L2 is the distance between the girder. This is going to be 6 meters. And then we have the L1 is the distance between the small beam is 1.6. That means the ratio of L2 of L1 is 4. That's larger than 2. That means the load transferring to the beam DI is going to be the one-way action. And by doing this, that means the whole area going to be the rectangular shape, and then the load on the beam DI going to be uniformly distributed load. What is going to be the value of the load? The value of the load will compute by the area of the floor that's cover the beam, and since it's uniformly distributed load, so we're going to consider only 1 meter. For the 1 meter of this area, it's going to time the distance that the beam gonna takes the load for. So the distance going to be what? It's going to be half of 1.5 and another half of 1.5, because the load going to divide half to another beam and another half to another beam, and then you get this distance of 1.5. So it's 1.5 times 1 is going to be 1.5 square meter, and then each square meter have the loading of 4.5. So the uniformly distributed load for the beam DI going to be 6.75. And since the beam is assumed to be simple beam, we let I is the pin and D is the roller. And then if you summation of the force in the x direction, the I sub x is 0. For the D sub y and I sub y, since the load applied on this beam is symmetry, then the D sub y will be equal to I sub y, and going to be taking half of the total resultant force. So the D sub y is equal to I sub y and equal to 6.75 kilonewton per meter times half of the beam DI length, that is 3 meter. We get the resultant of 20.25 kilonewton acting on the point D and on the point I. Okay, let's come to another different beam is on the edge of the building. By being on the edge, the area that's the beam taking care of will be reduced from half of the beam DI. So we can model the beam as point H, the green beam, acting by the force half of 6.75 due to its taking care of only half of the area. So the applied force is going to be half of 6.75 is 3.375, and then the reaction H sub y going to be half of 20.25, so it's going to be 10.125 kilonewton. By doing this, let us come back to consider the girder A, B, C, D, E, F, G, H. The girder going to subjected to the reaction from the green beam at H, and the beam at A gonna apply the same reaction to the pink beam. That is going to be 10.25. However, there is the beam on the other side also is going to distribute 10.125 at point A. So that means at point A there is 10.125 and 10.125. At point A gonna have 20.25 kilonewton force, and it is going to be the same as point H. Again, come to the beam DI. The beam DI apply the reaction at D of 20.25, and there is the beam on another side. So the pink beam going to get the load of 20.25 and 20.25 at point D. So at point D, we have the force of 40.5. So the model of the beam A, B, C, D, E, E, F, G, H is going to be this two force of 20.25. Okay, and the author gonna be 2 times 20.25. It's going to be 40.5. All of them 40.5, 40.5, 40.5, and 40.5, and 40.5, and 40.5. And again, since the beam is in symmetry, summation of x sub x is equal to 0. So h sub x is 0. And then the a sub y and the h sub y gonna take half of the total loading on the pink beam. So what is going to be? It's going to be like this: 20.25 times 2. That's mean the grid. And then we have the total of 6 pink beam. That is 6 times 40.5. And then the total divided by 2. We get the force of 141.75 kilonewton, transferring to the column at A and transferring to the column H. Okay, that's quite simple one. And then there is another problem that we should consider is for the beam that's subjected to two-way action. Then come to the frame of the timber house that have the floor plan as shown here. We assume the beam again constructed by the simple beam, and the force subjected to only the live load of 1.92 kilonewton per square meter. On this problem, the A is going to be 1.8. A is the distance between the small beam by doing this, and B is going to be the distance between the girder or the large beam. So the B is going to be L2, and the A is going to be the L1. So this problem we have 3 over 1.8 for the ratio of L1 over L2. So that means the ratio is going to be less than 2. This problem is going to be two-way action. And then they ask us to determine the uniformly distributed load that acts along the beam BG. And then they also ask us to find the loading acting on the beam A, B, C, D, and then we need to draw the picture and do the calculation for the reaction of these two beams. Okay, I suppose to make a note again about the blank of the floor over here. They are intended just show us the whole structural framing of this. In actuality, the floor gonna cover all the area here. Okay, coming into this, since the ratio of L2 is the distance between the girder and the girder, L2 is 3, and L1 is 1.8. So this guy is less than 2. The floor gonna have two-way action, and by two-way action we take this distance of 1.8. This is AB and this is HG. So this one is 3 meters. The distribution of the two-way action based on the experimental in the lab is shown that the crack of the slab under the loading gonna have the shape like this, in which the angle here is 45 degrees. When the angle here is 45 degrees, this is 45 degrees, and this is 1.8 meters. So it's going to take half of 1.8. It's going to be 0.9 and 0.9 meter. When this one is 0.9 meter, that means this one also 0.9 meter. So we get the triangular shape like this. That means the HG is here. Part of the HG gonna have triangular loading. And for the side of AH, the AH is here. Okay, when this one is 0.9, this one gonna be 0.9 also. And since the total length here is 3 meters, so the middle portion of this slab gonna be 1.2. And then the force that acting on the beam here gonna have the shape like this. And since the distance here is 0.9 and also another one beside it, so the total area that's cover this beam BG gonna be 1.8 meter. And then the shape of the loading gonna have the shape like this. And then 1.92 kilonewton per square meter need to times 0.9 for this one side, and another side another 0.9. So you get the force of 3.46 kilonewton per meter on the beam BG. And since the beam is simple support and have no horizontal force, so the reaction, the horizontal reaction is going to be 0. And since the beam is in symmetry, okay, half of the loading transfer to B and another half transfer to the G. So what is this? The length here going to divide by half. So the first portion here is going to be 0.6 times 3.46. And the area, the triangular area here is going to be 1/2 times 0.9 and times 3.46. The total is going to be 3.63 kilonewton, both at B and at G. Okay, now the B gonna have the loading of 3.63, and the C, since the C have the same loading area as the beam CF have the loading area the same as the beam BG, so the reaction at C is going to be 3.63. For the beam AH that take the loading area only one size, so that means the A and the D also going to have the reaction half of 3.63. Okay, so this is going to be half of 3.63 at A and 3.63 at B and 3.60 at C and half of 3.60 at D. And don't forget the triangular load that's going to apply at the interval AB, interval BC, and CD. So the model of the beam ABCD going to be like this. This is half of 3.63 at A and also SD, and 3.60 and 3.63 at B and C. And the triangular load have the distance of 0.9. So the magnitude of this triangular load is going to be 1.92 times 0.9 is 1.73, and all of them are equal. Finally, you can find the reaction that transfer from the beam ABCD to the column at A and the column at D. Again, half of the load acting on this beam gonna transfer to A, and half of the load going to transfer to the D, and you can compute the reaction to be 7.78 kilonewton at A and at D as shown. So at the end of this, I like to conclude that there is two types of load transferring. One is one-way action. Another one is two-way action. How to check it? You got to check the ratio L2 over L1. L2 is what? L2 is the distance between the big beam or between the girder or between the main beam. And the L1 is the distance between the small beam or the joists. If it's less than 2, the load distribution gonna be two-way action. If it's larger than 2, the load distribution gonna be one-way action. On the one-way action is simple. The floor gonna transfer the uniformly distributed load in the rectangular shape acting on the beam, and then the reaction of the beam will be transferred to the larger beam or the girder. However, for the two-way action beam, the distribution of the force from the floor gonna take triangular shape and also take this shape, okay? And the small beam gonna have this kind of loading according. For the girder or larger beam, the load gonna be more complex. And you may see that we can draw the shear diagram, moment diagram of this beam, but it's going to be harder than the uniformly distributed load. But I encourage you guys to try to draw the shear diagram and moment diagram of this one. However, for this one, the shear diagram and moment diagram is going to be tougher. So what's it going to be in reality? For me, after I get this beam, I will assume the distribution of the loading on this beam going to be uniformly distributed. Then I find the Vmax and Mmax, and I transfer the force back into this big beam, and then I also assume the triangular loading to be the uniformly loading. In this way, it's going to be make it easier to analyze, to find the maximum shear, to find the maximum moment of this beam. Anyway, due to the computer coming to us nowadays, it's going to be a lot easier to put this model into the computer, and we can analyze this kind of loading easily. Okay, let me finish the review of the first half of the chapter 2 analysis of determinate structure at this point, and I will go further to the second part.